for the electron. So that is not possible. Okay, these are the three things that we have learned till now. And next, another important point is we are saying that matter exhibits wave nature. Matter exhibits wave nature. When I say that matter exhibits wave nature, let me tell you, it is not single wave. Matter is not a single wave. It's actually a collection of huge number of waves. Okay, and all of them combined together will get you a new wave. Okay, I don't know okay, whether you understood or not. Okay, now for a moment we will keep that aside and see the see the picture as it is. Whatever you see on the screen. Okay, look at that. Okay, this picture is taken from OpenStax University Physics, all volume, something like this. Okay, this is the address. Okay, so whatever I take and wherever I take them from, okay, I just give these initiations also, or see representations also. Okay, wherever I don't give them, okay, that implies I have collected from 2 3 places and I summed up. Okay, so okay, when you superpose all these one, two, three, four, 5 waves, when I superpose all these waves, I get this kind of a resultant wave. Superposition of these 5 waves will be like this. Sir, will it be really? Okay, yeah, it will be. Now, is it really possible? Can we see that? Can we, I mean, can we learn that? Yeah. Okay, you can. Now, how can I learn that, sir? Okay. Yeah, you can learn that in your okay electronics lab. Okay, you will have CROs. Okay, you can superpose the 2 waves and try to see what resultant wave you will get. And then, if at all, if you are technically, I mean, if you learn technically sound aspects of it, try to club 2 or 3 together and try to see what will be the resultant output. అంటే 4 5 combinations చేసి resultant ఇవ్వచ్చు. Okay, you can see, okay, you can do, okay, only if at all if you have interest and if at all if you can use your technology there. Okay, so this is a proven fact that okay superposition of all these things will give you a resultant wave like this. Okay, so what, sir? So what? Yeah, good. What you see over here is that there is a small region of space where the amplitudes are very very large, okay, very strong, and there is some region where the amplitude is okay almost all dying off. Okay, so where I superpose a huge number of waves, I can make sure that this region has got a very very huge number of wave. Okay, that implies high intensity and amplitudes, and immediately there may be possible that adjacent to it you may lose okay the amplitude. That means amplitude may become zero. Okay, sir, that may be the case, but what are you trying to tell us? What are you trying to tell us? I'll come back to this. This is what you call it as a wave packet. Okay, this is what you call it as a wave packet. That means there is some region of space where you have okay the amplitude of the waves of superposition which is not equivalent to zero, and there is some other region where the amplitude is almost all becoming zero. Okay, now this figure is explained in the right side adjacent one. Okay, now this is the combination of 1 2 3 4 5 6, okay, almost all 30 kind of waves, 30 kinds of waves. Okay, simple harmonic waves. Okay, in the previous case 1 2 3 4 5 waves are taken and superposition gave you this. Okay, now I may be taking 30 waves like that and superposing. When I take 30 waves of that of like this and superpose, what I got is I got okay this resultant amplitude to be very large at one particular point and almost all zero. Okay, besides it only 30. If I take 100, it may be much sharper and as I said become much smaller. If I take infinite, then it may become a single pass spike and other things may become almost all zero. Sir, what are you trying to tell us? I'm trying to tell you that superposition of waves, okay, when I consider a huge number of waves superposed together, then I may get a particular region of space where the resultant amplitude is non-zero, and adjacent to it, the resultant amplitude may become zero. That's what can clearly be seen in this, okay, right side picture. Superposition of all these things, waves, wave is giving me a beautiful spike here that implies very, okay, large amplitude, that implies intensity, and adjacent to it the intensity is almost all zero. Okay, now I have been talking about intensities and all those things. Okay, now I'll change it to the matter waves. Okay, now this statement as I given over here, matter wave is a superposition of infinite waves of different frequency and velocity. Okay, in brackets I gave phase waves. Okay, I have to call them as phase waves. Okay, so you have a particle, that actually particle is made up of infinite number of waves which are superposing one another and having different frequencies and velocities. First point. Okay, now they are superposing, next statement, okay, they are superposing in such a manner that the amplitude is non-zero in the region of classical space. Sir, what is this region of classical space? Nothing. Okay, now you may be having a pen in your hand, or you may be having a book in your hand. You know that, okay, between two fingers you have the book. That means between these two fingers there is, okay, the object, and beyond that there is no object. But a wave should be existing in a very very large space, or maybe going to infinity also, right? So a wave may be going to infinity, but a particle has a definite region of space where it exists. That definite region of space where it is existing is what I am calling it as classical space. Okay, right? Now, okay, after that, understanding that word, that is classical region of space, what we say is we are superimposing huge number of waves, and because of the superposition of huge number of waves, okay, or infinite number of waves, the superposition may result in such a way that the amplitude is non-zero. The amplitude is non-zero, as I show, okay, over here. The amplitude is non-zero. Amplitude is non-zero in the region of classical space. In the region of classical space. In the region of classical space. Okay, here. Okay, particle. Okay, in the region of the particle. That means wherever the particle is existing, there the superposition is non-zero, but everywhere else, okay, it is giving you zero amplitude. It is giving you zero amplitude as you see in this figure. This way, you can say that matter wave is nothing but a collection of infinite number of waves which are superposing on one another and giving you, okay, a non-zero amplitude in the region of classical space, or to say in the region where you have the particle, and it is giving you zero amplitude of the wave, okay, beyond those particles. That means, okay, after the particles existence, that means particle is existing, let me say, from point A to point B. Okay, beyond point A and beyond point B, the amplitude of that superposition of those waves is giving you zero. That is a very beautiful aspect that you have to consider and remember with regards to wave packet associated with matter waves. Okay, and anyway, resultant, okay, this is the resultant wave. Okay, this is the resultant wave. Okay, right? Okay, anyway, the resultant wavelength. Okay, when we talk about wavelength, okay, when we talk about wavelength, okay, you will be talking about the resultant wavelength. Okay, resultant wavelength. Okay, right. After coming to, okay, after that, let us come to this point. As I said, this is a superposition of infinite number of waves, and superposition is such that, okay, in region of classical space, the amplitude is non-zero, and beyond that it is zero. So each wave is moving with a different velocity, and this is called phase velocity. Okay, so the phase velocity of matter wave is greater than c. Okay, this is something which you might have not come across earlier, but this is something which is beautiful. Okay, phase velocity of matter waves is greater than c, whereas group velocity of matter waves is less than c. Okay, remember that. Okay, this will be asked in 1 mark answers in bits or so. Okay, so phase velocity, that implies independent waves might be moving with velocity which is greater than c, but as a collection, they will be moving with velocity which is less than c, and that the group velocity is your particle velocity. The group velocity is nothing but your classical particle velocity. That is Okay, we said that chalk piece is moving with 1000 meters per second, right? So the group, okay, the group of waves that is actually constituting, okay, that actually makes up your chalk piece, the group of waves which make up your chalk piece actually move with a group velocity which is 1000 meters per second, but the phase velocity, that means independent waves, might be moving with velocities much greater than that, or okay, usually greater than c. Okay, that's a very important aspect that you should remember or understand here.